Okay, our next talk will be enhancing groundwater management capabilities using Python. And we have with us Alyssa Balzan, who is a hydrologist with KT Groundwater. So please help me welcome Alyssa.
Our happy hour reception, so thank you for being here still. So a common theme in this conference has been we collect the data, but what do we do with it? That is the key. We have to do something with our data. So KT Groundwater has created 3 tools that can help you maximize the data that you have worked so hard to collect. Before we begin, I want to give a huge thank you to Clearwater Underground Water Conservation District and Middle Trinity Groundwater Conservation District for investing in our tools, which utilize and maximize the data these districts have obtained. We know how much effort the districts put into collecting their data, and we greatly appreciate Clearwater and Middle Trinity for taking this to the next step to generate reproducible means of analyzing that data. I know most of you are already familiar with the big picture. Desired future conditions are one of the major aspects of groundwater management in Texas. KT Groundwater wants to streamline and improve those processes for managing your DFCs and aquifers. To do that, we have created 2 tools using Python to help get you there. We have also created a 3rd tool that helps in visualizing aquifer drawdown when processing well permits. These are our 3 tools: the drawdown tool, the aquifer status tool, and the aquifer data analysis tool. Just like any code, there are bugs, and you may see some in these slides because these tools are still under development. However, we do work closely with the districts to try and fix errors as quickly as possible when they find them. The tools were created to enable districts to utilize their data. To give you a brief overview, the drawdown tool allows the user to look at the impact of a proposed well. The aquifer status tool allows the user to view aquifer-wide and aquifer-specific water level trends. And the aquifer data analysis tool incorporates water quality data. I'll present each of these tools, but we'll start with the drawdown tool. So imagine you have a permittee submitting their permit application. They provide you with a well location, the annual production rate, the discharge rate, and their proposed aquifer. So your big questions are, how is this going to affect the neighbors, any surrounding wells, and how is this going to affect the aquifer? To answer these questions, you can use our drawdown tool. It's fairly simple, and it has 2 sections. I'll zoom into these a little bit more on the next slides, but I just wanted to show you the overall page. It has the input section at the top, then a map, and then at the bottom is a table of wells. In this input section, you'll enter the well location, your maximum search radius, which determines the contours generated around that proposed well. You'll also enter the production rate in acre-feet and discharge rate in gallons per minute. We use both of these values to capture short-term and long-term trends in the aquifer. The reason that we have transmissivity and storativity as optional is because although it is ideal to use these values from groundwater pumping tests, if you do not have data from that proposed well, this tool will pull on the GAM data and automatically fill in that transmissivity and storativity value for you. You'll also select your proposed aquifer, and then you'll hit submit. This is what the tool will generate. You can instantly see the groundwater might react to that proposed well, and it allows you to see many different scenarios. At the top, the transmissivity and storativity values from the GAM that were pulled for this particular proposed well scenario are displayed. And the contours here are generated for 1 year of drawdown. A maximum search radius is generated, and any wells within that search radius that are within the proposed aquifer are highlighted for you. A table is also generated that shows the drawdown of the proposed well at the top and any wells within that search radius, again, that have been highlighted. The one-day drawdown is using the gallons per minute discharge rate, while the other time periods use the annual production rate. We'll review the next two tools together because they're much more similar. So the aquifer status and aquifer data analysis tools are more comprehensive management tools that allow a district to track DFCs. Within both tools, a DFC summary page displays both the adopted and annual DFC and calculates water level trends within each aquifer. The average current trend is the average of all calculated trend values for an aquifer, and the median current trend is the median of all calculated trends for an aquifer. We also have the ability to display the current status of the aquifer compared to the DFC. So if your aquifer is, water levels are within the DFC, we can display that as well, or not within the DFC. These tools also display water level trends for each individual well, and these tables can be filtered by aquifer. The checkboxes on the left side allow you to turn off a well so it's not included in the overall trend calculations. This gives the user ability to introduce nuance and their best judgment if something doesn't look right, or if they know a particular well has inaccurate measurements. So let's say that you have a monitor well, you know it has a hole in the casing, and there's water from a different formation pouring into the well. That's not a great situation, but it can happen, and this could artificially inflate the water levels, so you may not want that well included in your DFC trend calculations. On the Aquifer Status Tool Water Levels page, you can click on a well from the drop-down menu, and it will populate this hydrograph with the water level measurements for that well. Well details are displayed below the hydrograph, like the well location, the aquifer, the depth, highest and lowest water level recorded at the well, and water level changes. The map also highlights and zooms in to the selected well so you can see exactly where it's located. You can filter water levels by date, and the hydrograph differentiates between static and pumping water levels. You can also turn off those pumping water levels using that toggle button at the bottom, so that helps if you don't want those showing on the map. However, the trend values, the trend lines are calculated based on only the static water levels. It also displays a turning point line, which was calculated using RDP. And this simplifies the trend line by only considering when the direction of that data path changes considerably. The last portion of the tool is the contour map. The map is optimized using caching, so you don't have to sit there and wait for it to load. The contours are already generated, and you choose the year, the aquifer, and the contour interval, and the contours will display on the map. These show depth to water from the land surface. This is the contour map for the Aquifer Data Analysis tool. This map also allows you to toggle between depth to water or water elevation. And this particular district uses management zones, so you can turn on or off those management zones, as well as using turning on or off faults in the area. A table of water level measurements that was used to calculate this will also be displayed underneath the map. Lastly, I'll show you features that are only available in the Aquifer Data Analysis tool. This tool has a well analysis page, and this page displays details for any of your selected wells. You can filter by date, and trends and statistics about that well and the water level data are shown in the table. For example, you have the well use, well location, and then the total number of water level measurement records for that well. You also get a water level data table that displays the highest and lowest water levels, the historic largest change, and slope as well. A well diagram is generated for your well if you have that information. and you can view the screened interval, the diameter of the well, as well as any geologic formations. A hydrograph also displays the water level measurements and shows a trend line. These pages include a map which highlights and zooms in to the selected well, and a water level measurement and trend table are also displayed. On the spatial analysis page, you can view the slope for the current date, which will display all the historical data, or until the end of the DFC, so from 2010 to 2080. This hydrograph shows the median water level difference of water levels over time. This is the middle value of water level change for a particular year. Displaying it this way prevents the values from being skewed by extreme highs and lows, and it shows the typical rise or fall of water levels over time. The last page is water quality. On this page, you can select a water quality parameter that you like to view, and then the second drop-down will automatically populate with any wells that already have that water quality parameter available. So you don't have to spend time scrolling through every single well, clicking on it and hoping, oh, maybe this one has TDS values. So it'll narrow that down for you and help save time. This tool also generates a plot of the water quality data and also displays the water quality measurements in a table. The map zooms in on on your selected well, and then a stiff diagram is generated for the well also, which displays the ionic composition of the water sample. We made these tools using Dash, which is a Python framework for web applications with interactive data visualization. The tools are designed to work with any data format. So regardless of who your database provider is, the tool can work with your data. The tool packages the file, and it can be run on any computer from anywhere, and it runs directly on your web browser. The drawdown tool uses the Tice equation to calculate drawdown at different distances and times, and then displays those results as concentric circles within a defined radius. The contour maps were created with ordinary kriging to interpolate water levels between existing wells. A spherical model was chosen, and ordinary kriging was used because it produces smooth contours with more influence closer to the center, with influence lessening as you increase your distance. We estimated trends using the Thielsen regression, which chooses the median of the slopes between each pair of points in the data, and it also minimizes outliers. Turning points were calculated using RDP, which is the Raymer-Douglas-Pucher algorithm. Pandas was used to work with the data sets, and GeoPandas enhanced this by allowing us to do spatial operations on geometric data types. NumPy was used for supporting arrays and matrices, and mathematical functions to perform calculations on those arrays. A GeoJSON format was used in the tools because it allows us to store geospatial data in one central structure. Plotly is a graphing library that was used to create those interactive graphs, and then we used Mapbox to create the interactive maps. The calculations done in these tools are based on several assumptions, which does limit the accuracy of those calculations. The Tice equation assumes that aquifers are homogeneous and isotropic. So if water is moving one direction in one way over here, it's going to be doing the same over here. We know that that's not the case in real life, so this is a significant assumption that this equation makes. It also assumes there are no complex geologic conditions like faults or groundwater flow boundaries, and that input parameters are accurate. So the calculations are only going to be as good as the data that you put into it. If your transmissivity and storativity values are coming from the GAM, those are not considered data because they're just estimates. If you had transmissivity and storativity values from pumping tests, these would be much more site-specific, so that's definitely preferable. For slope calculations, slope regression ignores outliers, so it may not capture a non-linear trend. It's also important to have, again, high-quality, consistent data. These tools are not going to substitute for site-specific numerical modeling or groundwater pumping tests, but they are great screening tools to give you an overall idea of how the aquifer might respond to pumping or estimated, and also to estimate historical trends. To summarize the three tools, the drawdown tool answers the question of how might the aquifer change. The aquifer status tool looks at change over time, and the aquifer data analysis tool looks at change over time and water quality. These tools are not a database or data management system. They are tools that work with your data to make it accessible to your personnel. There are a lot of opportunities to enhance these tools, including integrating them with telemetry so that the tools can update their calculations in real time. The trends could also be separated to view seasonal versus long-term trends. Predictive modeling could be integrated, and water quality change could be mapped. We could also integrate correlating water levels and water quality change, or create a function that allows you to generate custom reports. It's also a good opportunity to make it more mobile friendly, so maybe this is something you might use in the field. And K2 Groundwater is also working on a second tool for Clearwater written in Python that creates an interface with the groundwater availability models. These tools are very customizable, and we can tailor them to whatever your district needs. The key takeaway I want to impart to you is that you can monitor aquifer status for DFC compliance using these tools. They produce reproducible, defensible, and data-driven results. Before I close out, I asked ChatGPT to create a comic of a day in the life of a hydrogeologist using our tools. And this is what it came up with. I would like to note that I am a stickler for spelling, and I specifically asked it to spell correctly. So we know that you cannot rely on AI for spelling. So probably not much else either, but maybe with some improvements in the future, that'll get better. So. Thank you again to Clearwater and Middle Trinity, and also to Mike, Philip, and Michaela for their work on these tools. If anybody's interested in a demo, I'd be happy to go over that with you after this. Thank you so much for your time, and does anybody have any questions?
Any questions for Alyssa? Fascinating. Any questions? All right, well, let's give her a hand. Thank you so much.
Thank y'all.